Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Well, another great problem here where we still considering Bohr's model. And as you may recall, Bohr's model deals with the atomic orbitals and energy levels. And in our problem here, we are considering the case where the electron and the proton in the hydrogen atom are bounded together by the gravitational force. So instead of the electrostatic force in the original model, we will now see this model will be affected if we use the gravitational force, how this will affect the energy levels and the atomic orbitals in our case here. So one thing to remember, and maybe the main assumption of Bohr's model, is that the angular momentum is quantized. The angular momentum is quantized in the following manner. L is equal to nh bar. So the angular momentum is referred to here by L, and N is the principal number and takes an integer values, and h bar is reduced to Planck constant. So this will be our main task here, to find an expression for L, solve for the energy and radii in terms of the quantities that we can measure. So let us start. The first thing that you may proceed with here is that this is a semi-classical model. So applying Newton's second law will be a very good idea here. What Newton's second law tells us to do? The sum of the forces, remember, if this force, I will label them I, the sum of the forces acting on the system is equal to ma. However, this is, in our case here, we are dealing with a circular orbit, so a here will be v squared over r. So this is mv squared over r. I will refer to the position vector from the origin. I will take the origin to be here at the proton, to the electron here to be r. And by the way, the proton here is assumed to be fixed, and this is not a very good, not a very bad assumption. Now we have the sum of forces is equal to mv squared over r. And what is the forces acting on the system? We said in the very beginning that we will consider only the gravitational force. So let us see how this works. The sum of the forces will be reduced only to the gravitational force. And this is equal to mv squared over r still. What is the gravitational force? We know this. We know the expression for the gravitational force. It's Newton's law of gravity. So this is equal to J. The gravitational force between two particles is equal to J, the mass of the first particle, the mass of the second particle, over r squared. It's an inverse square law. And they both are in the radial direction, so no worries about the directions here. Let us rewrite this equation. Let us rewrite this equation. We will use Fj equal to Jmb m sub e over r squared and equate this with mv squared over r. Now, by the way, this is me, since this is the moving particle here. Me. Okay, so J mb me over r squared over r squared. This will be equal to me v squared over r. A nice cancellation will happen here, and we end up with the following. The r cancels with r, and me cancels with me. And we end up with v squared. Let us leave it as squared here. So this is J mb over r squared. Wonderful. Over r, sorry. We will box this relation here. Now we have an expression for the velocity. We still need to get the angular momentum. Let us move to another board here. So the angular momentum, remember, is equal to what? Is equal to the position vector r cross with the linear momentum b. What is the linear momentum here? It's just mv, and all this are vectors, so no worries about this here. In a circular orbit, when you are working with a circular orbit, the angular momentum will be just rmv. Why? Because the position vector, which is r here, will be always perpendicular to your linear momentum here. Here's mv. At any instant of the motion, they keep an angle of 90 degrees. This is a tangent to the circle, and this is a radial position vector, so they keep an angle of 90 degrees, and you end up with the cross product reduced to the regular rmv. Well done. So this is our expression for L here, and we have the main postulate told us that this is equal to nh bar. However, we already have our expression for v. Let us rewrite this here. So v square from the previous part is equal to what? J, remember, mb. I'm just copying the expression that we have before. J mb over r. And by the way, this should be r capital as well. Now, very good. We can take our v here and substitute with r. Or we can do this the other way around. Let us make this v squared. So squaring both sides here. I will call this equation 1, equation 2. I will squaring 1. Squaring 1 will give us what? R square, m square, and of course, let us keep our labels. This is me. The electron is the one that has kinetic energy associated with it. So this should be me here. And times the velocity. This is squared, this is squared. All this is equal to nh bar squared. So let us substitute from equation 2 for v squared. So this will be r squared me squared j mb m sub p here over r. Okay, and all of this is equal to n squared h bar square. So we can get an expression for r, the atomic orbital, the radius of the atomic orbitals. So this r cancel with this r here, and we end up with the following. R is equal to what? N square h bar square. Sorry, let us write it here again. N square h bar square over j me square mb. Wonderful. This is a very important relation here. Let us keep it in mind. So we can substitute with the numbers here and get a feeling of how this r will be. However, let us leave this to the very end here. And by the way, let us give this a label. This depends on the value of n. So for n equal 1, we have a given value for r. For n equal 2, we have another value. So we should label this r here. Let us call it rn, r sub n, referring to the n equal 1, 2, 3, and so on. So far, so good. Now, let us take the analysis one step further and see how we can get an expression for the energy levels as well. Can we do this? Of course we can. Let us use another part here. So Remember, in Bohr 2, we get an expression for the radii in terms of the principal number, the masses, and J, the gravitational constant. Let us now try to find an expression for the energy here. So the energy, the total energy of the system is equal to what? It's the kinetic energy, 1/2 mve square. By the way, let us remove this label. This is E. We have assumed that the proton is fixed, so there's no worries about the kinetic energy of the proton here. And the potential energy, I will write it down, and please, if there were any questions and how we got this is from classical mechanics. Just let us know. So the gravitational potential energy here can be found using the following relation. If you are interested, you can try this. This is fj dot dr. So if you make this integral here for the force dot dr, you get the change in potential energy. This is how we find this expression here. This is not our main task here, so let us back again. So we have our expression for v squared so far. So good. Let us rewrite this expression in terms of the let us substitute for v squared here. So 1/2 me times v squared, which is what? J, remember, mb over r. And you discover something very neat here. Those two expressions are exactly the same except for the 1/2 here. So you end up with the following. This total energy will be equal to minus 1/2 J me, me mb over r. Wonderful. We have found an expression for the energy. And if you recall, just a slide back, if you go to slide 2 here, we have found an expression for r here in terms of the quantities that we said before, right? The principal number, h bar, and the masses, and j. So let us write the energy in terms of these quantities as well. Why not? So this will be minus 1/2 J me mb times 1 over r. So all this will be multiplied with what? J, let me write it down directly. I'm just copying from the previous slide. So Jm square mb over n square h bar square. So n square n bar h bar square. So this is equal to what? This is equal to minus j, let us write it, j square mb square. We have made something huge here. We have found an expression for the energy levels in terms of the masses, the gravitational constant, and the reduced Planck constant. And of course, as before, this is n square h square, by the way. As before, let us call this En to refer to the value of the energy that correspond to this n here. For n equal 1, we have the ground state, n equal 2, we have the higher states, and so on. To get some feelings for the numbers, let us substitute here with the numbers and see how this energy and radii will be. Let me box this relation here. Very important relations to remember. I will use another port for this. So let me just introduce another port here. For the radii, let us consider the ground state, only the ground state. Let us start with the expression for R. R1 here means we are making, so let me call it R capital as we did. So R1 will be equal to what? Will be equal to h square over j mb. So R1, we will replace n with 1 here, is equal to h square j mb me square. So far, so good. So we have all these values known. So for h bar, it's 1.06 times 10 to the negative 34 here. And it has the units of joule second. Let's write this down. And all this is squared. This is over what? Over j. J is known to be 6.67. There's very small numbers here, and this will make all the difference, by the way. So Newton meter square over kilogram square. And this is times 1.67 times 10 to the negative 27 kilogram. 27 kilogram times this for the mass of the proton here. Finally, the mass of the electron will be 9.11 times 10 to the negative 31 kilogram. And all this is squared. Well, just plug these values into your calculator and you end up with this value here, 1.2 times 10 to the power 29 meters. What a huge number we have here. And this is expected from the very beginning, by the way, because we are dealing here with a very weak force. You can see that this kind of values will come up in your end results. As this is an extremely weak force, it cannot hold the electron and the proton together. So you end up with the first orbital 10 to the power 29 meters away. This is very, very good values to consider here. This is these values give us an intuition of what we can expect from the gravitational force. And for the energy, we will have the following. E1 is just minus j square, right, mb square me cube over 2h bar square over 2h bar square. And this is equal to what? This will be a long expression here. However, for j, we will have 6.67 times 10 to the negative 11 Newton meter square kilogram square, all this is squared. And this is times, let's write it down here, 1.67. This is the mass of the, so in our case here, it's a 1.67 times 10 to, this is our standard values for the protons at mass. Oh, sorry, this is to the power 10 to the negative 7 kilogram. And this all is squared times 9.12 to 11 times 10 to the negative 31 kilogram cube, and all this is divided by 2 for this factor here times h bar square, which is 1.06 times 10 to the negative 34 a square as well. Of course, this is joule second, as if you are considering the units here, this is joule second. If you make all these calculations, if you plug in the numbers, you will find that E1 is equal to what? Minus 4.17 times 10 to the negative 97 joules. Wow. Very small number, very tiny amount of energy, even a very fraction of the thermal aggregation will be able to move this electron away from the first energy level. This was all for this problem. Let me summarize what we have done here very quick. We have the Bohr's model. We have considered this using the gravitational force instead of the electrostatic force. We have solved for the velocity using this Newton's second law. Then we have found an expression for the angular momentum. From this, we found an expression for Rn, the orbital radii here, and another expression for En. And we get a rough idea of the values here in both cases. For the ground state here, we found the value of R1, and the ground state, we found the corresponding energy as well. We have it turns out to be very small amount of energy with very huge radius. This all comes out from the fact that the gravitational force is extremely weak and cannot bound those particles together unless you have a very huge radius with a very tiny amount of energy. This is the energy, of course, of the first level here. You can compute whatever you need. The formula extends to from n equal 1 to infinity, and try to work out the numbers and see how it goes with you. Have a nice day, and thank you.